Hello everyone, my name is Peter Lyons, and this is Lab 4, Oscillations, with Dr. Schatz's Physics 2211 class at Georgia Tech. So, in this lab we're going to observe a weighted mass at the end of a spring on a fixed point, and then we will compare the motion with Newton's second law and the energy principle. We will examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring, and then we will observe a computer model that analyzes the energy principle of said motion. After all is said and done, Newton's second law and the energy principle were upheld. Here we have our good friend Dr. Greco, who has just attached a weight to the end of a spring and the other end of that spring to a fixed attachment point shown here. We've set the origin to be that said fixed attachment point and our calibration sig to be 0.7 meters, which is the length of the spring with the weight. Now you press play, you can see Dr. Greco release the weight on the spring, and it moves in almost a circular motion, showing that the x and y values are oscillating between two specific points. You can see the graphs in the top right. As time gets longer, x and y both move in a sort of wave format. Alright, so here's the formulas that I used for solving for our unknowns in the equation. We had to figure out what the spring constant was, along with what the resting length of the spring was, which we found the spring constant K to be 6.87 newtons per meter, and the length of the spring at rest, or L naught, to be 0.127 meters. And right here, below that are the various formulas that I used in my code, with kinetic energy being equal to 1/2 mv squared, the gravitational potential energy equal to the mass times the gravitational force times the y component of the object, and the spring potential energy being 1/2 k times the length minus L naught, and then energy being the sum of kinetic energy and gravitational potential energy and spring potential energy, and then the energy principle, which is always equal to 0 and is equal to the change in kinetic energy plus the change in gravitational potential energy plus the change in spring potential energy, and the equation to find the period t, which is equal to 2 pi radical m over k. Let's run our computer model. Now you can see we have a yellow ball, which is where the fixed point of our model is, attached to a light blue spring, which is attached to a blue weight. We also have a red ball, which is our tracker data, that is following the blue weight very closely. The only reason that the red weight is a little more jumpy is because the time step is much, much larger than the computer model. We have a black arrow representing gravity and a blue arrow that is representing the spring force. We will examine this graph on the right in further detail in the "What does it mean" section of the video. So, what does this all mean? Is the energy principle satisfied in this example? Now, looking at the graph we have from our computational model, you see we have an oscillating red line, which represents the spring potential energy, an oscillating green line, which represents the gravitational potential energy of the system, and an oscillating blue line, which represents the kinetic energy of the system. And you see a yellow line that is not exactly at 0 the entire time, but it pretty much goes along the 0 line across the entire time interval, and that's the sum of all the energies, which is all equal to 0. Since that is equal to 0, then the energy principle is satisfied. And how do the periods in the x and y direction differ? We found the period for the x direction to be 1.71 seconds and the y direction to be 1.52 seconds. Now, the only reason why these two differ is because gravity acts in the negative y direction, but it does not affect the x component of the speed of the spring. So the only reason that these have two different periods are because there's an asymmetry of forces acting upon the weight in the x and y directions.